discuss about this. Okay. Okay, Assalamualaikum again. We'll be continue discussing about this force on current carrying conductor in magnetic field. Okay. So, continue. If I have a magnet north and also south, okay, and I put X. So using your Fleming left-hand rule, basically, you know it will be forced down. Okay, but how? Okay, let's see. So the magnetic field pattern for magnet is always north to south. The magnetic field pattern for X, which is current flow in, as we discussed before, it will be in clockwise rotation. So if you compare the magnetic field at the top and the magnetic field at the bottom, you see that at the top is in the same direction, at the bottom is in different direction, means the force or magnetic field at the top is stronger than the bottom, so the wire will be forced down. So using your Fleming left-hand rule, you will also get the direction down. Okay. So how you want to determine the north pole, south pole, and X? Okay, without using your Fleming left-hand rule. There's one way. Okay, one way is by remembering just one. Just one meaning if you see north, south, and X, this one force at the bottom. Okay, force down. Because if you have question like this, especially in trial, they always will ask you something like this. Okay. So what is the pull? This one at the top, and what is the pull at the bottom? Okay, most of students can't answer because most of the time they rely on the magnet. Okay, if you remember north south X bottom, north south X bawah. Okay, north south X bawah. So kalau kita rotate, if you rotating this, okay, if you're rotating this, you will see that south pole is at the top, north pole is at the bottom. So this is one of the popular question in trial Mrsm. Okay, this is one of popular question in trial Mrsm. So if you remember just one, it'll be enough for you. Okay, so let's see the question. So the application is this one, motor. Okay, so DC motor, direct current motor. As discussed before, you need a battery and find the direction of current flow. So current flow to the left here and flow in this side, and this side is flow out. Okay, based on what we have discussed previously, so north and south and X for flow in, dot for flowing out. So remember one, north, south, X to the bottom, the other side will move up. So this motor will rotating in anti-clockwise rotation. Okay, if I change the battery, what happened? So it will rotate in the different direction, which is clockwise, right? So we see the question. Stop sharing this. We move. Okay. Okay, so stop sharing this first. Let's move to the question that I gave you yesterday. So this one. Okay. Okay. So diagram show a current carrying conductor placed between two magnetic pole, right? Even there's no battery here in the picture, you see this word, current out. And in which direction will the conductor move? In which direction will the conductor move? Okay, D. Alright, good. Ada any other answer other than D? Okay, good. D. So, like I told you, I always ask a student to remember one, meaning like this: north and south, X, bottom. Why I always ask to remember X? Because most of the question in XPM involving X, meaning current flow in. Okay, this question that you answer is from the trial examination. So they change the X, which is current flow in, with current flow out. Right. So if I remember this, meaning, so if I have a dot, it will be in different direction, up. But this one is north at the left, south at the right. Equation given is north on the right side, south in the left side. So meaning you're rotating it. So if you're rotating the picture, that means you're rotating the picture, so it will show you to the bottom. Okay, so there's two ways to make in a different direction or different direction of force. The first one, either you change the battery. Okay, change the battery, the direction, positive and negative. The second one is by change the pole of the magnet. Okay. So second one, this one. Okay. Diagram show a current carrying conductor placed between the two magnetic poles. In which direction will the conductor move? What is your answer? North, south, and remember, this is X or dot. Okay, so because current flow out meaning this one is dot. So north, south, dot at the top. North, south, dot at the top, because we remember north, south, and X bottom. So north, south, dot will be in different direction, which is up. Okay, so you see the wire will not, okay, the wire will not be forced to move in between the magnet. So the answer for D and B will never exist. So it will always move out of the magnet. Okay, always move out of the magnet. Will never move in between the magnet. Okay. So the second one is this for the motor. Okay, for the motor. So this side, actually, even this motor, okay, DC motor or direct current, the way to answering it is still same. meaning you need to know which side is flow in, which side is flow out, and you can find the direction based on just one direction. No need to know in both directions, because if one side is moving down, the other side will move up. They will never move like both up, both down, no. So if one side, you know, moving out, moving down, the other will moving up. So example here, okay. So if you see here, north, south, and this side is flow in, so this side I put an X. The other side is out, out, so this side I put a dot. Okay. The one that we remember is north, south, X, the bottom. But this picture showing you the other side, which is, it will show you this north, south, for X, move up. So meaning this side is moving up, surely this side will moving down. Okay, so then you know what is the rotation. So the rotation is in a clockwise rotation. Okay, it moves in a clockwise rotation. Okay, so this is quite challenging for most of the students. Actually, same thing. You need to know where's the current flow, because there's a picture of battery there, so you need to know where's the current flow. So based on the picture, this is the positive, meaning current will flow here, here, and into the back. Okay, into the back. So the very basic is like this. You know, this is north at the top and south in the bottom, and flow from the front to the back, flow in. So which is the direction? Because we have already remembered north and south and X to the bottom. Okay, so try to rotate. So where is the direction? Either it move to the left or move to the right. Okay, so in the picture, if you're rotating this, you see that X will show you here to the left. So the answer is A. Okay, so therefore you don't need actually to use your Fleming left hand rule if you remember this one. Okay, no need to do like this anymore. Okay. All right. So before I go to the induction, there's one question in paper 2. Slide down a bit. Okay, this is the question. Okay, you might refer to the note I'll giving you yesterday. Okay, same thing. So know the current flow here. This is the front here, here. So current flow from the front to the back. So current flow in. And then show you a current flow in at it being pushed out this side to state the polarity of a permanent magnet in the diagram above, right? So based on the picture, you know it's like this. It doesn't know the pole of A, doesn't know the pole of B, but thinks that you know this is X. So korang tahu yang ni X. How you know that this is X? Based on the current flow. And this one being pushed this side. Okay. What we have remember is north and south and X bottom. Okay, so what is the pull for A and B? What is the pull for A and B? A is south, B is north. Good, Fazrin. Good try. This is south and this is north. Why just rotating it? You rotate and you know which south and which north. Okay, good. A is south and B is north. So that's the first question. State the polarity of a permanent magnet. So A is south and B is north. Good. So name the rule used to determine the polarity of the permanent magnet. What rule do you use? You use a Fleming left hand rule. Why you know it's left? Because there's a battery, a wire, and a magnet. Okay. C, state the way to reverse the direction of motion of wire in diagram above. How you want to reverse the direction? Instead of being pushing out, you want to push it into the magnet, in between the magnet. Okay, push to the left. Before this, push to the right. So how you want to change the direction for the wire to be pushed to the left? Okay, there's two ways. What is it? Change the direction of battery, change the polarity of magnet. Okay, good. Okay, thank you, Najwa, Akasha, and also Fazrin. That's a correct answer. Excellent. The first one is changing the polarity of magnet. The second one, you also can change the direction of the battery. Direction of current flow. Okay, good. Good, thank you. That means you understand. Okay, this one. Based on the picture, based on the following aspect, give suggestion on how the wire can be swung higher. So meaning you want the wire to be having a greater force. Okay, to be having a greater force. So basically, to have a greater force, there's also three ways. The first way by increasing the current. The second way by increasing the number of turns. You see, same like the first one, electromagnet. Same thing. The third one is by using a stronger magnet, or in other simple word, by adding more magnet to increase the strength of the magnet. Okay, so based on the following aspect, suggest how the wire can swung higher. The number of magnet, increase the number of magnet. So Akasha wrote down in the chat, increase the number of magnet. Good. Increase number of magnet. Okay. The reason why? Because you want to increase the strength of magnetic field. Okay, to increase the strength of magnetic field. All right, number two, the diameter of a wire. Okay, what you want to change in the diameter? So what is the relationship between the diameter and current? Aina answering smaller. Okay, another one is increase diameter. Okay, so which one? Right, this one, basics in electric. If you remember electric, there's a 4 factor for resistance, because you know if you have higher resistance, you will have lower current. So to increase the current, you need to produce a lower resistance. So resistance depend on 4 factors. The type, length, okay, length, if longer length, lagi panjang wayar, higher resistance. But diameter, if you increase the diameter, the resistance will be lower. Okay, another one is temperature. Alright, so the diameter, what you need to change the diameter? You increase the diameter. Okay, you increase the diameter. Why increase the diameter? To reduce the R resistance, or you can also to increase the current flow. Okay, both is acceptable. Okay, it's okay, Aina. People make mistake. Okay, we learn because we learn it from our mistake. Don't worry. Okay, good try. So this one is last one for this subtopic. Draw the resultant magnetic field produced by the DC motor. Okay, how you know motor? First, you know this one, the battery there. And how to draw. Okay, how to draw. This one, I want to teach you how to draw. Okay, first, tell me what is the direction of the wire on the left and wire on the right. So which one will be pushed up and which one will be pushing down? Okay, you can put it on the chat. Which one will be pushed down and which one will be pushed up? So what happened to the dot and what happened to the X? So which one pushing out, which one pushing down, based on what we have learned before. Dot push out, okay, dot out, okay, good. Dot push out, okay, good. Christina, Fazrin, Akasha. So this one is pushing out, meaning if this is up, the other one is down. And we remember already north, okay. What I asked you to remember is north, south, X, down. So the other side will be up. Surely will be up. Okay, good. So then how to draw? Okay, to draw, first you need to draw the magnetic field. Okay, I use a blue color. Magnetic field from north to south, from north to south. Put the arrow north to south, north to south. First one. Okay. If the wire being pushed up, meaning the magnetic field at the bottom is stronger than above. So you can also draw like this first. You can also draw like this first. Okay. So then you draw like this. Okay. Now you see the magnetic field at the bottom, there's a 4 line, and up as only 2, meaning magnetic field at the bottom is stronger than the top. So the wire will be pushed up. So to the right side for the X, the above magnetic field has 4 lines, meaning stronger than the bottom, which also only have 2 lines. So that's how you draw the magnetic field pattern. There's 2 marks for this. Okay, there's 2 marks for this, 2 marks question. Okay, good. So basically done for force on current carrying conductor in magnetic field. So you need to remember which side is flow out, which side is flow down based on the current flow, the first one. The second one is you need to know how to draw the magnetic field pattern. And the third one, what factor is affecting the magnetic field pattern. If you know both 3, that's enough for you actually. Okay. Okay, Next, we move to the most confusing subtopic for most of the students. Basically, it's not confusing at all. Okay. So as I told you earlier, the difference between this subtopic electromagnetic induction and force in current carrying conductor is, first, you see there's a galvanometer here. Okay. So when there is a galvanometer, meaning the wire doesn't have a current that flow. Okay? There's no current flow. Because in electromagnetic induction, we want to produce the current. We want to produce the current. Or we call it also, we produce the energy. Also, sometimes they call it induced EMF. EMF is basically a volt, okay, or energy. So you want to produce an electric energy. Basically, in the simple explanation is, we want to produce a current or induce EMF. By how? By cutting the magnetic field. So electromagnetic induction is production of induced current. So induction is production of, okay, my pen doing induced current when there is cutting of magnetic field or magnetic flux. Okay, production of induced current when there is a cutting of magnetic field or magnetic flux. So meaning you want to produce a current. You have a magnet. Okay, you have the magnet and you want to produce the current. Okay. This one. Okay, I share with you this induction. Okay. So in induction, you have a wire. Okay, you have a wire. You want to cut the magnetic field, meaning you need to move the wire. Either you move up or you move the wire down, up or down, up or down. Okay. So the other way is to move the magnet. Okay. So because we say cut, you need to cut. Okay, you need to cut. So if you want to cut something, like you want to cut an apple, okay? If you cut an apple, what you do? You put an apple on the table, so the apple is static, doesn't move. You move a knife, then you cut an apple. The other way to cut an apple is you put your knife, okay? Then you move an apple between the knife, so it also cut an apple. If you put knife, okay, on top of the apple and you move it together, so there will be no cutting of an apple. So same thing here. If you want to cut the magnetic field, one is moved, one is not. Or you can move both in different direction. That's another way. Okay. So in Lenz's law, in induction, you need to use Fleming right hand rule. But the most important in this chapter is not that Fleming right hand rule. The most important is to understand what is Faraday's law and what is Lenz's law. Okay, what is Faraday's law and Lenz's law. Okay, so I give you here Faraday's law and also Lenz's law. you can jot down this in the region I give you. Okay, so Faraday's law state that the magnitude, okay, magnitude maknanya dia punya strong, kekuatan magnet, kekuatan voltage tersebut or current tersebut. Magnitude or EMF directly proportional with the rate of cutting magnetic flux. Okay, I put you in a simple word. The simple word is like this. You move or you cut it faster, you get more current. That's what Faraday says. Okay, so the difference is like this. You have like this. This is a galvanometer. This is a galvanometer. So you see the difference. The difference is one showing a value of 3 ampere. Okay. The second one showing you a value of 1, which is 1 ampere. So 3 and 1, which one is bigger? Number 3 or number 1? Surely number 3. So that means 3 is the higher magnitude. So magnitude basically is nilai. Okay, nilai. So 3 and 1, 3 has higher magnitude. So comparing 3 and 1, 3 has higher magnitude based on Faraday's. So you know that 3 ampere, the cutting of magnetic field is stronger. Okay, so that is Faraday's. So how to make the magnetic field, sorry, how to make a current flow ataupun the induced current bigger? There's 3 ways. First, increase the speed of cutting. Second one, increase number of turn. You see, increase number of turn, a factor for all we have learned. Electromagnet, force on current carrying conductor, and also induction. Increase the number of turn. And number 3, use stronger magnet. Okay, use stronger magnet. So this is for Faraday. Faraday talk about the magnitude. The magnitude is directly proportional with how you cut the magnetic flux or magnetic field. So the higher magnitude mean higher speed or higher number of turn or use a stronger magnet. Okay. So another one, Lenz's law. So this is important, Lenz's law. So Lenz doesn't talk about the magnitude. Lenz talk about the direction. Either the galvanometer show you to the left or showing you to the right, that's a Lenz's law. So Lenz's law, the direction of induced EMF is always opposed the direction causing it. Okay, so to understand this, there always a question like this. Okay, always opposed. What is the meaning by always opposed? Okay, here we have a magnet. Magnet move into the solenoid. Okay. So when magnet move into the solenoid, you need to see the direction of movement. Okay, first you need to see the direction of magnet move. Because if it move towards the solenoid, okay, like this one, it move towards the solenoid, solenoid will oppose. Solenoid tak nak, dia nak tolak, dia tak suka magnet ni. So in order for the solenoid to push the magnet, this side should be a north pole. Okay, this side will be a north pole. This one, okay. Magnet doesn't move to the solenoid, it moves from out of the solenoid. Okay, move away from the solenoid. So when it moves away, okay, to oppose the movement, we want to attract it back. Kita nak tarik dia pula. Bila dia datang kita tak nak, bila dia dah tak nak kita nak kat dia. Okay, macam orang kena ngorat. Waktu kena ngorat tak nak, dah kena reject baru nak. Okay, so north pole and south pole. North move away. So when move away, you want to attract it back. So you want to attract this back. So this will be south. This will be north. So first step is for you to determine which one is north pole and which one is south pole. So that's the first step. The second step is you use your right hand grip rule. Okay, right hand grip rule. So remember, thumb always show to the north. So for the first picture, my thumb is to the left. My other finger is from front to the back, front to the back. So meaning this one, I pointed on the solenoid front to the back, front to the back, front to the back. So they will be to the back here. So this will be the direction of induced current. So galvanometer will show to the right. Okay, let's see the second one. North pole moving away. So the north pole here for the solenoid is on the right. So it will be like this. So my other finger is from the back towards me, from the back to the front. From the back to the front, so I follow the finger direction, which is bottom. So galvanometer will point to the left. Okay, pointed to the left. All right. So we have 1 minute. We need to give you another ID after this. But before that, you have a question. I give you a question of paper 2 related to this, related to Faraday's and Lenz's law. You might try it first, and I see you back in 5 minutes, and we discuss on the topic, which is for Faraday's law and Lenz's law, and also an induction. Okay. Okay, this kind of question in paper 2. Right, this is from a trial, Mrsm trial examination. You might try it first, then we discuss